Lots of exciting stuff happening in this video. I'm a little hesitant about this one, guys, because it's going to be very math intensive, and I'm the guy who actually failed algebra and had to retake it. So it's with a little bit of hesitation that I present a lot of equations, a lot of math intense type of stuff. So I hope that you can help me through it. If my notation is wrong, whatever else, I hope it's not so wrong that it's tedious to look at, because what we're working with here is something very dynamic and something that's very beautiful to me. We're dealing with prices in a moneyless system. One of the great things about the free market system is that it can assign prices in real time, and it can reflect values as they shift. It can reflect demand and supply as it shifts, and it's this dynamic, beautiful, intelligent system. But it's not perfect. And what this system tries to do is not only maintain all of the strengths of the free market pricing system, but build upon them. Right now, our pricing system is not very indicative of sustainability. Just because you can go out and buy a can of tuna fish for under $1 does not necessarily mean that the means to which we process that tuna is completely sustainable. The system that you're about to see does inform us of that. It's a more intelligent system than the free market system itself, meaning that it does inform us of a variable that we can extrapolate and inform us of the sustainability of a particular product or resource. So, without further ado, here it is. This is what I was working with. This is a little bit more complicated than what it was in the original paper. That's because when I started working with it in the original paper, or from the original paper, I found out it was a little too simple and not very useful. So I've expanded it a little bit here, and I've changed some terms, so we'll go by these quickly one by one. P, of course, we're talking about price. D is demand. We were talking about in terms of sort of an order system. If you could imagine everything on Amazon suddenly being free, you go out and click whatever you want. We would then have a total tally of what people would want, and say like the wish list these days. That's kind of how it's actually done. You can click whatever you want. My wish list is a little different from your wish list, and so on Amazon. Demand is going to be just an aggregate count of those orders of whatever particular product or resource we're dealing with. C is cost, and I know what you might be thinking is that, wait, how can you have cost without money? Well, the fact of the matter is, if you take a cup of water out of a gallon of water, the cost of that action was a cup of water. And there it is. So we're talking in terms of costs of the resource itself. If it was a widget, we would then break down all the necessary parts of that widget and translate that into the cost. How much wood does it take to build a house? How much metal? How much this? How much that? And then all the energy it takes into actually processing things or shipping the materials or whatever it might be. That's cost. The second part of the top part there is really a measure of sustainability in terms of renewal rate, the rate of renewal. We're going to take a look here at a little experiment, a little simulation of a real world working moneyless economy and how this pricing system can actually fluctuate and change in real time. And renewal is something that our present system doesn't really take into account. So this is an interesting part. The bottom here is really taking into account the supply of the previous cycle to keep the whole thing linked together and intelligent with itself. This whole system really is built on what I'm calling a cycle, in which a bunch of things happen. Orders are counted, processed, resources of course are depleted in the processing of those orders, in the production of those orders, shipping of those orders, so on and so forth. Those resources are renewed as much as our technology allows, of course, or natural runoff maybe in terms of water, whatever the case may be. It tracks how much we renew per cycle and then calculates the price. And so the price is then generated at the end of the cycle so that people who approach the market during that next cycle have an idea of where things are going. And once we gather enough of this kind of data, it can create a little bit of a graph that is very informative of what is happening in the society and what kind of steps should be taken. So we're going to pretend now that we're all in a moneyless society and are using this particular system and to see how it works. And we'll take a look at some numbers and some graphs. So here they are. What I did for this is, and I'll pull this up on my screen, is I created a little bit of an experiment where demand was determined by a dice roll. So the demand could be between 1 and 6. I gave us sort of an arbitrary starting amount of resources of 100. The rate of renewal would be 3 units per cycle, and the cost per demand, meaning that what you order is going to be costing 1 of the unit of whatever widget or resource that we're dealing with. Simple stuff, but it gets the point across. So in cycle 1, I rolled the die and had 3. Well, 3 just happens to be exactly what we replenish the system with each cycle. So it just so happens that the price is 0. Why? Because the resulting supply is exactly the same as it was before. We hit the absolute sweet spot here. And that's really what we want to see. We want to see as many zeros or as close to 0 as possible. The next cycle, we rolled a 5, meaning that there are going to be a demand of 5 within this particular cycle. And as we know, 5 actually outsteps our rate of renewal by 2. So we actually have to draw upon our supply, our reserves, in order to meet this particular cycle's demand. The price that is generated at the end of the cycle is 0.03. It's bigger than 0.0 because we're drawing upon reserves, and it gives us a starting point as to where prices are going or where the demand is going, and if we need to rethink our system in terms of this particular resource, whether we need to up our rate of renewal, whether we need to up our our amount of what we can supply, or perhaps create a better widget that uses less resources, so it taxes the system a little less. Going through the rest of the cycles here, the ones that are really interesting here, you can see that the highest it gets is in cycle 7, where it's 0.06. We're putting a lot of stress on the system. There's a demand of 6, there it is, and we're drawing from a supply of 95. So we're actually looking at the resulting supply of cycle 6. We're drawing from that with a demand of 6 in cycle 7, and we have the highest price of this particular experiment. The two other ones that are noteworthy, of course, are going to be this cycle 6 and cycle 9. Well, you can see they're actually negative numbers. And what's so interesting about this pricing system is that it does not act like a linear roller coaster like money prices do today. Rather, this graph can be best read and thought of as an elastic band. The more you stretch away from center, the more stress is on the system, either in the positive or the negative. The positive we can understand. We're actually drawing from resources. What's interesting to consider is that if we stretch too far into the negatives, it means that that demand is so low and our rate of replenishment is so high that we might be able to use some of the capital in this particular system. Capital meaning means to production, or whether it's pipelines or warehouses or whatever it might be, generators, whatever, might be better used in other areas. If we drop too much into the negative, it means we're overdoing it. We have available capital to reallocate based on a wider system of more graphs like this. So then let's think about what a town hall meeting might consist of with this particular graph, this simple little graph. If I was to approach all of you good people about this, and this happens to be, say, water in our little society, and keep in mind, we could create this in a very small society of just 5 volunteers or so. Size doesn't really matter. But I would approach all of you and I'd say, look, ladies and gentlemen, we have a situation here where the cycles are indicating that demand is oftentimes outstretching our rate of renewal. And you're not seeing many negatives here. We're not replenishing much. And if this doesn't change, we are going to run out of our supply. And as you can see, we are in the positive so much that when we do jut up into the positives, those points are a little bit higher each time, a little higher, a little higher, a little higher, and so on and so forth. this isn't good. In order to change that, we need to think about ways to either up our rate of renewal. We need to either produce more water somehow, or be more intelligent with our filtration systems to somehow get water back into the system so that we're replenishing it at a greater rate than 3 per cycle, because 3 per cycle right now isn't working for us. We could see that perhaps we could, use less water. Let's say that this isn't just drinking water, but this is water that's needed for hydrating a crop of some kind. We could say we could develop a better way of hydrating that crop and use less water, and that would help this graph as well. That would help this particular system. But what's important about all this in this make-believe little situation is that policy making now all of a sudden is based off of very objective material instead of, oh gee, what should we do? I think this, I think that kind of bullshit. This is actually, it's numeric. It's right there in front of you. It's very easy to take a look at. And once you get used to looking at these particular graphs, you get to the feeling, just as we said before, it's more of an elastic band sort of an idea, rather than, oh my God, there goes the price. It's a boom and bust cycle. You can't really read it that way. What we're going for, of course, is to equal everything out, to hit 0, so that we're taking just as much as the system is replenishing, and we can track sustainability on that. Much better than we can with our current system. So, there it is. I hope it was easy to follow. A little bit longer than some of the videos, but there it is. I hope it was worth it and worth the content. Tell me what you think in comments below. Any critiques, any ideas that you have. If you recreate this particular experiment, send me your video responses. Of course, I will accept them and upload them here to the channel. Make sure that they are connected to the channel, however that works anymore. And voila. Thank you so much.